Hi everyone, today we are going to do a super quick video on residual vector quantization. I'm hoping that you already know what vector quantized variational autoencoders are. If you don't, I will put a card here for the video that I made previously on that and a link below so you can go take a look at that. I will be writing very little code today because really not a lot has changed between the VQVAE model and moving on to residual vector quantization. So today's more of just a understanding of what is residual vector quantization, why do we use them, and why is it so popular in speech architectures, right? So in a lot of encoder type or encodec type models. So we're going to take a look at that in just a bit. But let's go ahead and first talk about, or just kind of recap again, what was vector quantization and why do we do it? Vector quantization is the process of taking a continuous signal and mapping it to some type of discrete state. So let's actually just make this a little bit bigger so it's easy to see. So let's make this maybe 800. There we go. Right, so here we go. So the process is we want to take a continuous space and map them to k number of discrete codes. And k-means clustering is exactly what this does, right? When you have some data, you fit your k-means clustering model on it, and the model will identify k number of codes that it will use, right? So these are these x's are the k centroids that it identified as these are the centroids I'll have. And that means everything inside these regions is mapped to that code. So it's kind of like rounding, right? If you pass your continuous data to your model, it'll find, okay, which region does it belong in? If it's in the red region, then it can be anywhere in here. And then it just rounds it to the nearest code. And this is exactly what k-means does, and this is exactly what the VQVAE model was doing, except in VQVAE, we're essentially just training the codes concurrently. It's trained in a different way than how k-means is trained. But either way, in the VQVAE architecture, we're looking for discrete codes to map the continuous outputs of our encoder from, right? So again, if any of this sounds a little bit confusing to you, just go take a look at that video where I talk about it in more detail. So the residual vector quantization is essentially just an update to this idea. And here's the critical idea of what's going on. In vector quantization, when we take, let's say, everything in this red region and we map it to a single centroid, right? A single centroid of that region, then you can imagine that you now have an estimation error or a rounding error, right? Like this point right here is represented by this cluster here. So the distance between this point and this cluster center is a rounding error. And so in vector quantization, we just hope that we have sufficiently enough codes to kind of not have this issue. But this may not be the correct way of going about it. Like we still have error, and this is expected, right? This is expected because anytime we're rounding a number, because that's all quantization is, it's just rounding to something, then you're going to have some error, right? You've lost that additional precision. And so residual vector quantization is a method of trying to maintain this precision a little bit better. So the way you should think about it is, again, it's a standard autoencoder model. You have a input, it encodes it, right? It encodes it, and then you get some continuous output. That will go to your autoencoder, so kind of like this, right? You have an encoder, encodes it, you'll get some continuous vector. And then this continuous vector goes to some code book, and in the traditional vector quantized method, let's make this picture bigger too, just so it's a little bit easier for everyone to see. There we go. There we go, yeah. So in the traditional VQVAE, we had an encoder, we got some embedding. This embedding went to some type of a code book. We then grabbed the closest code, right? Because that's what we want. And then we passed that closest code to our decoder, and that was it. But now what we want is to have a better estimation of what something is. So instead of using one code book, what if we use multiple? And so the procedure goes kind of like this. We have an input, we encode it, so here we go. Again, same thing. We go to our first code book, we quantize it, find the closest code to this continuous representation, and we grab it, right? We grab that. And then what we do is we take the original code and subtract this from here. We subtract our quantized embedding from here. And all we're left with is the residual, right? So again, if we took one of these, let's say this is the continuous output of our model, right? This point right here. If we take this and then subtract the cluster center, which is the code that we identified that goes with that specific value, the specific point, then if we subtract this from this, then all you're left with is the distance between the two. And so that is us basically storing our residual. That's the residual, the error that we're missing. So me taking my continuous embedding and subtracting the identified quantized token, right, from our codebook, computes a residual. And what we do is take this, and that produces a new vector, right? We produce a new vector that is essentially the residual, or the difference between the original continuous and our first step of approximating it with this code. And now we just rinse and repeat. We're going to essentially take this residual code vector. So now know that this is the discrepancy, how much it was off by. We quantize the discrepancy again, get a new code vector, right? We just repeat the same process, get a new one, again, subtract it. And now we get a new residual. And every time we repeat this over and over and over again, we essentially get a collection of these quantized tokens, right, from each codebook. And then our final estimation of the original code vector is just going to be the sum of all of these, right? Because again, these are just residuals. We're hoping the sum of this plus this plus this will closely approximate the original continuous vector while maintaining our discrete codes. We just have multiple discrete codes now instead of just having one of them, right? But that's the key idea, right? In VQVAE, we had a single codebook. We quantized our embedding, the continuous embedding, we got some quantized token, and we passed it to the decoder. But like I just mentioned, that leads to some type of an estimation error, right? Because there's always a distance, right? Some error that we had between the identified code vector and the point that we're essentially rounding to, right? The point that we're rounding to that code vector. And so let's just continuously quantize first on the original embedding, but then we quantize again on the residual, the difference between the original embedding and the first quantized token. That produces our estimation error. Let's quantize all the estimation errors on our data again. Again, we rinse and repeat. We get a new code vector, subtract, okay, we get a new residual. And then again, quantize it, and you get a new value, and just repeat this as many times as you want, right? Obviously, the more times you do it, the more code books you have, right? So it becomes more expensive, but you do it as many times as you want, and then at the end, we know that this value here is our original estimate for this, and then this is an estimate of the error, and then this is the estimate of the second order error. And so the sum of all of these will give us our final code vector, and we're hoping this is a closer approximation of the original embedding. The best way to understand this is from this figure. So see, we start with some points, and we identify some k-means clustering, right? We identify a cluster, then I subtract the cluster centers from every point. That creates a new thing. We do our clustering again. Again, we subtract our centers, and you can see every single time we do it, we're converging closer and closer and closer to zero because our estimation error gets smaller and smaller, right? Every single time we do it, we find the clusters, subtract the cluster centers from all their points, and then go ahead and identify the residuals. And then again, repeat, and then again, compute the residuals. As long as we do this over and over again, we'll end up having a good representation of our data, right? Just represented by multiple codebooks. So we still are quantizing our embeddings. It's just instead of using a single quantized embedding to represent a token or our continuous base, we're using a sequence of them. So what we're going to do today is just quickly implement this. So like I said, this is going to be a relatively short video. I am not going to implement anything for the most part new. We do need to implement the RVQ portion, but things that stay the same are our data is fine. Also, our vector quantizer did not change. Each individual quantization process, this whole thing here, none of it changes. For every codebook, we still do exactly the same thing. We identify the closest latent vector, right? The closest one. So we're just going to go ahead and copy that in. The only small difference that I added in was this. So we could have actually done this last time as well, but I didn't. Last time we only returned the quantized latents, right? So, the quantized embeddings from our codebook. But this time I'm going to return not only the quantized latents, but also the index, right? The index of which quantized latents from our codebook were actually selected, right? So we can actually quickly test this. Let's do, again, our VQ is going to be our vector quantizer. And let's say our codebook size is, let's say 512, and our latent dim is 8. Right, so there we go. And so we have some data that we're going to pass in. Let's do rand is equal to torch dot randn, and let's do let's say we have 32 embeddings, and each embedding is of size 8. And we want to take these continuous embeddings and, again, find the closest quantized token to these. Right? So let's go ahead and do that. We can do VQ and rand. And this will return the quantized embedding. So you can see here's for the first, actually, let's make it smaller. Let's do maybe 4 of them, right? So this is the quantized embedding for the first of our 4. So there's 4 samples, or 4 embeddings, each of them of size 8. So the first embedding was mapped to this quantized token. The second embedding was mapped to this quantized token, ... right? So those are the quantized tokens that were embedded, that we grabbed. And then here are the indexes. So this is me saying that the first embedding, continuous embedding, was mapped to the 55th quantized token in our embedding, right? Because our embedding dim has 512 of them, right? We set the codebook size to 512. So the first one goes to the 55th token. The second one goes to the 296th token, ... I'm only doing this just to show another thing. We could have done all of this in the VQVAE as well. There's just something cool that I wanted to mention, so we'll kind of get to that in a bit. But either way, nothing has changed. This is identical to the implementation from last time. We just have this additional return, but nothing else has changed. Okay, so now let's go ahead and just implement a linear residual vector quantizer, right? So we're not going to do a convolutional one. Not that a convolution would change anything. It's just redundant. I want to keep this video short and sweet if I can. So let's go ahead and do that. So we're going to do class linear vector quantizer, right? Linear vector quantizer. And let's call this linear residual, right? Because it's a residual vector quantizer. nn.module, just like every model. Good. And so first of all, init, and let's just tell it a couple things. So we have our latent dim, right? So let's compress down to 2 numbers just for, so we can, it doesn't really matter. We're not going to really plot anything today, but let's just do 2. We have our codebook size. Let's say we want 64 codes in every single codebook. And then the question is, how many codebooks do you want? Let's do num codebooks equals 4. Right? There we go. So that's how many codebooks we want. And so that would be essentially, from this figure, how many of these do we want in every single step? And so let's go ahead and now implement the rest of it. So this implementation will feel very familiar because, again, we haven't really changed much. So super init. And let's first do self.latentDim is latentDim. So we're going to store that. And let's go ahead and write our encoder, self.encoder. This is mnist, so you can literally write anything you want here, and it'll probably work fine. Sequential. And we're going to do a nn.linear. We reshaped our mnist image to 32 times 32, and we're going to compress to 128. And then we're going to do a relu. Then again, another linear layer. It's going to go from, let's say, 128 to 64. Again, another relu. Another linear 64 to 32. Oh. One more relu. And then lastly, we'll have our mapping to our latent dimension, nn.linear 32 to latent dim, right? So whatever our latent dimension we selected is. So there we go. That's our encoder. And our decoder will look exactly the same. So I'm just going to copy it, right? It's just the other direction, right? Going from the latent dim back up to 32 by 32, and then a sigmoid because our mnist images are scaled between 0 and 1. So there we go. Now let's go ahead and define the residual vector quantizer. And the residual vector quantizer is, again, just a collection of vector quantization, right? We just repeatedly do it over and over again. So let's go ahead and create that. We're going to do a quick self.rvq. It's going to be nn.module list. Module list. It's going to be a list of these vector quantizers. So let's go ahead and just create a bunch of them. It's going to be our vector quantizer. And we're going to pass in our codebook size, right? So how many codes do we want? Our latent dim, how the dimension of each of the codes. And we want for blank in range num codebooks, right? So how many of these codebooks do we want? And so if we go ahead and take a look at our model, let's take a look at it. Model is this. Print out our model, and you'll see we have a encoder, a decoder, and we have 4 of these vector quantizer modules inside. So there we go, right? Nothing too crazy. So let's go ahead and now write the rest of it. So let's first do the simple version, just trying to replicate what we did last time. And then we're going to add a couple of extra features just so we can start tying it to some of the speech architectures I want to get into in the future. But for now, let's do a quick forward function. So just like always, we're going to do a def forward self x. Our data is going to be some batch size by channels, by height, by width, right? Because that's just what it is. X.shape. There we go. And so like we're doing linear layers, so we're going to do x is x.flatten to make it a vector. So it's going to be 1024 length vectors, or 32 times 32 input length vectors, but we'll leave the batch size. And so the first step is we need to produce our latents, right? And these are going to be the continuous latents that come out of our encoder, right? The stack of linear layers. So we call this latents. It's going to be self dot forward encoder x. So let's go ahead and write the forward encoder. In this case, the forward encoder is very simple, so I didn't really need to do this, but it's fine. I'm trying to keep it the same as the last one. Forward encoder self x, and then we're just going to return x equals return self.encoder x. Right? So we just took our data x, and passed it through our stack of linear layers. And that's it. Nothing else has happened. This is just so we have easy access to some of the internal methods, but it's fine. It doesn't matter. We could have also just done it down here. Good. So that's step one. We have our latents. After that, we need to pass our sample data through the decoder. Right? So it's time for us to actually do the quantization. And so to do the quantization, we're going to go ahead and do that in the decoder portion. So let's just do a def forward decoder self x. And we can quickly create a, actually for now we can just leave that. We'll type that in later. Let's go ahead and do our forward decoder. So to do the decoding, we need to first quantize, right? So we have our latents. Let's go ahead and quantize our latents down to their discrete code vector. So this is going to be self.quantize x. And so we need to write the actual quantize function, right? That's basically what y'all are here for. So let's go ahead and write that. Quantize self. We're going to pass it z, which is what we're going to call our latents, right? And then I'm going to pass in an extra thing here. Return code index only equals false. And we'll see why we use that later on. For now, just kind of ignore it. So step one is we will create our, again, we still have the same codebook loss and commitment loss from last time, right? So remember in the vector quantized variational autoencoder, we have three losses. We have our reconstruction loss, we have our codebook loss, which makes sure that our, and we have the codebook and the commitment loss that just makes sure that our encoder is projecting to numbers that are close to the codes in the codebook, and then vice versa. We want to make sure the codes are moving in the direction of the encoder. And this is important because remember, we had to use the skip gradients, right? We basically copied the gradients across the non-differentiability of the vector quantizer. So we need to somehow estimate what those gradients are, and we used essentially that method. The codebook and commitment loss is our best guess of what those gradients would look like. There are other ways like dictionary update methods and stuff that we could use to update those code vectors, but for now we're just gonna stay with the default implementation. The only difference is before we had a codebook and commitment loss for a single quantizer, right? We just had one of them, but now we have multiple. So we're gonna just add up the codebook and commitment loss for all of the different quantization modules. And it's as simple as that. So we're just gonna create some variables here. We're going to call this codebook loss. Let's just make it 0. Commitment loss is also 0. And I'm going to create some lists here. Quantized codes. It's going to be a blank list. This is where we're going to store the quantized codes from each codebook, right? So we're going to keep them in there. And then we're also going to have our code indexes. Code indexes is an empty list. And that's where we're going to store the index of the codes for every single quantizer. And that's why we returned both the quantized and the closest, right? Because the closest is our indexes. Okay, good. So let's go ahead and let's set our stage here. We're going to create a variable called final quantized is going to be torch.zeros like z. So again, remember, our end goal is our final quantized embedding is going to be the sum of all of the outputs, basically the quantized tokens, from each of the codebooks. So what I'm going to do is just go ahead and create a 0 vector right? And then as I'm going through the code books one at a time, I'll just add them in directly. I could have also added them after the fact, right? It doesn't matter. But just for simplicity, I will create a 0 vector, and then as I'm going through one code book at a time, I will add those into here. And that will be in the same shape as Z, right? It'll be in the same shape as Z because we have, in this case, I guess we don't have data, but if we go up here, we had Z would have been a 4x8 vector. So basically we have 4 embedding, or a batch size of 4, each represented by a vector of length 8. And so we're just going to create a 0 vector, or a 0 matrix in this shape, 4x8. And then as we quantize each of these things over and over again, because each of these continuous embeddings will be quantized individually, as we quantize them one at a time, we're just going to, through all of different quantization modules, we're just going to accumulate them in. So we've just gone ahead and created a 0 vector here just to store, and we're going to just add to that as we go. So we're going to just loop through our quantizers. For quantizer in self.rbq, we're just going to loop through all our quantizers, and most of this will be very, very familiar, right? So we're going to get our codes, and code index is going to be our quantizer Z. So this is me passing my Z, my continuous embedding, into my quantizer, the specific quantizer right now, and it returns my my codes, right? My quantized codes and the code indexes. So that's what I got here. So there we go. That's step 1. After that, we're going to go ahead and just store these code indexes for now. We'll see why we need them later. Indexes.append code index. So there we go. And now we're going to go ahead and compute the VQ loss. So just like before. So first off, we have our codebook loss. And the codebook loss is going to be the mean squared error, torch.mean, between our codes and our Z. But if you remember, right, and this shouldn't be, this should be a minus, sorry, minus Z. But if you remember, doing this does not work because in a VQVAE, the getting the codes from Z is a non-differentiable process. PyTorch will attempt to compute a derivative like d codes dz or something like that. And that derivative does not exist. So you can't do this. And so what we're going to do is z.detach. So as far as PyTorch is concerned, and let's add the other parenthesis in, Z is a constant right now, and we're trying to minimize the distance between our codes and some constant value. And so this is going to make sure that whatever is producing our codes, specifically the codebook, moves closer and closer to the output of the encoder, which produced Z, without actually computing that derivative. It's just an estimation, our best guess estimation of that derivative. So again, commitment loss goes exactly the other way. Commitment loss. And this is going to be codes.detach, because we want it to be constant, minus Z, again, squared. So again, we want our encoder, Z, right, the encoder that produces Z, to move closer and closer to codes. But because we can't take the derivative, we're essentially just setting the codes as a constant, right? So as far as AutoGrad's concerned, this is just a constant value that we're trying to move our Z closer and closer to, right? So this is essentially the main idea. Now, if you remember in our commitment loss, later on, we're going to multiply this by 0.25 because we want to make sure that our encoder, our encoder still has flexibility. So its focus shouldn't only be just let's get it as close as I can to the codebook. On the other hand, the codebook should definitely be trying to move closer and closer to our encoder. So there we go. That's our setup there. Same as before, nothing new. So let's go ahead and do codebook losses plus equals codebook loss. So we're just going to accumulate up our losses for each of our codebooks. So then commitment losses plus equals commitment loss, just like that. And now let's go ahead and do our straight through estimation. So if you remember, later on, our decoder is going to get we need to pass the decoder the codes, right? We need to pass decoder these codes. But these codes currently don't have any gradient information from Z because there's no way to do it. So we have our straight through estimator where we do codes is equal to Z, which seems ridiculous, right? That doesn't make any sense. So we're going to do plus codes minus Z dot detach. So what we've done here is, first of all, if we got rid of this detach, what we wrote is codes, let's update that, codes is equal to Z plus codes minus Z. So all I wrote is codes is equal to codes. As far as the computation, like the numerical values, is concerned. But as far as AutoGrad is concerned, we can compute DZ decodes here because DZ decodes is 1, right? It's just 1. Or decodes DZ, right? The derivative of this would be 1. So it doesn't break AutoGrad, but it allows me to copy gradients from future steps in the chain rule back to the encoder. So again, if you're confused on any of this, I talk about it in a lot of detail in the VQVAE implementation, but for now this should be fine. And so we all have our final quantize. So this is the important part. It's going to be our final quantized plus codes, right? So I got my first set of codes. So what you can imagine is I have this vector here, and I've initialized it as zeros. And I finally have computed this value right here, this code here. So I'm going to go ahead and just add it to this 0 vector here. And then when we do it again, we're going to grab this one, and then we're going to add it to this, not 0 vector anymore, it has the previous one, but we're going to add it to this one, and we're just going to repeat this over and over again. We're just going to keep adding our estimation every single iteration. And so now that we have that, we've gone ahead and added our codes, our current estimate of the codes to it. We can now go ahead and do our quantized codes. Quantized codes is going to be, and we can go ahead and store .append codes. Right? Let's go ahead and store those codes as well. And so now we have everything. We have stored our codes that we got from this specific codebook. We have computed our final quantized vector, at least up to the specific code. We have gone ahead and done the straight through gradient. We've computed our losses. We've accumulated our losses into here. And we're kind of good to go. Except we still have one step left, and that's the residual part, right? What we want to do is take our codes that came from the codebook and subtract it from our original estimation of the continuous vector, right? So we want to take the continuous vector that we started with and then subtract our codes from it, and that produces the residual. And then when we do that, we can basically repeat that over and over again as we go forward. So let's go ahead and do that. We can just write very simply, we can write very simply our z, right? Z is the thing that we started with. We're just going to take z now, and we're going to set it equal to z minus our codes. And so what I've done is I've taken my original z, I subtracted the codes from it, and that produces my new z. And so z is now the residual of my original z and my current estimation for the codes. But do you see a problem here? If we had done this operation here in PyTorch, this won't work out, because this again will try to compute a dz decodes, right? There's a derivative happening here, dz decodes, that we can't do anything about. And that was exactly the reason we did this, right? We did all this work here so we could avoid doing that dz decodes derivative. But again, here it's finally returned. But as far as z is concerned, codes is just a constant, right? It's just a constant we're just removing from our existing z to compute our new residual to pass into the next step. So we can just go ahead and do .detach, right? We can go ahead and do a detach here, and this will go ahead and compute our residual and just loop through them over and over again, and we are done. That's basically the entire novelty of the RVQ, this one line right here, right? And the idea of looping through a bunch of these code books. So let's go ahead and do if return code index only. So if you only want to return the code index, what I want is, if we have 4 code books, I will have each code, right? Each vector, so each embedding in z. So if we only have one vector in z, this one vector, if you imagine, let's just go back to the picture. Oh. You can imagine that if we pass in this one vector for z, what I want is the index of, okay, in the first code book, what embedding did I pick? In the second code book, what embedding did I pick? On the third code book, what embedding did I pick, right? Or the index of the embedding that I pick. So we just want to go ahead and store those. And we have those, right? We know that right here, we have our code indexes. We never really used them, but we stored them. So let's go ahead, and if we're only returning these code indexes, then let's just go ahead and stack them together and we'll be good to go. So we can just return torch.stack code indexes, what do they call it? Indexes. And we'll do it along the last dimension, right? So we just stack them horizontally, and there we go. We have now just returned our code indexes. We'll talk about why we do this in just a bit. Otherwise, right, we'll just return everything else. We'll do our final quantized. We'll return our codebook losses. We'll return our commitment losses. And that's it. I think that's basically it. So that essentially is the implementation of the RVQ, as is, nothing crazy. And now what we're going to do is just add two more methods, just some quick methods that will be important. But actually, let's go ahead and wrap this up first. So we have our quantizer. When we're training, this is what we want anyway. We don't really care about this flag right now, so just ignore that. When we're training, we're going to return all these things back. We have everything, and then we will pass our final quantized, right, which has been the accumulated up encodings from all of the different quantized modules, quantization modules. Let's just go ahead and pass that through the decoder. So to do that, we just do decoded is equal to self.decoder final quantized. And then we can go ahead and return everything. We'll call this final quantized. We'll have our decoded, we'll have our codebook losses, and commitment losses. So there we go. We have now written everything out. We'll get back to the next part later of like why did we add this extra flag in just a few moments. For now, let's see if this just works. So I'm going to just copy this example here. This should probably work fine. I don't need you. I guess I called the model slightly different in my thing. Looks like we have a bug. Get codes rand. Okay, I might have just spelled something or done something wrong. We have our get codes. Oh, okay, actually, we haven't even written that method yet. Okay, so we're going to do that in just a second. Let's just pass into our model our rand. There we go. And so we can check here if we print our latents, latents.shape, we have our embeddings, right? So we've gone ahead and stored here, right? So we have our 2 by 2 because for every single sample, we're representing it by a vector of length 2 because we decided that our latent dim should be 2 and we have 2 images. So that's our latents. And now what we're going to do is take these latents and pass them to the decoder. So we're going to do all of this stuff, right? So all of this stuff will get returned is going to be equal to our self.forward decoder, and then we're going to pass it our latents, just like that. Okay, now it looks like we have a bug. Codebook losses, so spelled something wrong. Let's quickly fix this. Codebook loss. Yes, so codebook losses. What did I call you? Let's just make sure. Yeah, so that's what I called it. So we'll have losses and losses. Okay. Yeah, it looks like it didn't throw a bug this time. So we can print out our final quantized dot shape. And there we go, right? That's our estimation. We also have our decoded, right? So we have our decoded values there. We have our codebook loss, losses. Looks like it's incorrect. So we have our codebook losses plus equals codebook loss. Let's just check here. Codebook losses. Okay, there's all of the losses. So it looks like I didn't, oh wait, did I print out the shape? That's my bad. Yeah, it shouldn't be the shape. There's no shape. There we go. That's our codebook loss. And then similarly, we'll have a commitment loss, right? So there's our commitment loss. And so there's everything ready to go, everything we would need for training, right? Everything that we would care about for training. So let's go ahead and just send our decoded back to our original image shape. So decoded dot reshape, and we'll put it in batch size by channels, by height, by width, print decoded dot shape, and we have our image shape back, and everyone is happy now. So we can go ahead and finally return our latents. We can return our final quantized. We can return our decoded, our codebook loss, and our commitment loss. And that is everything. Again, I spelled something wrong. Let's codebook losses, commitment losses. So there we go. That's everything. So that is us just returning everything, and we are good to go. So we should be able to just train this model now without any issues. So let's go ahead and I'm just copy pasting the training script from last time because nothing has changed, right? It's the same training script. We get the same information, same codebook loss, commitment loss. We do the same 0.25 constant. We have the same reconstruction loss. Nothing new has happened here. So we can just go ahead and quickly train this model just to make sure it does something reasonable. And I called this without the VAE. Oh, I guess I called it something completely different. So let's just double check. Linear Residual Vector Quantizer. Maybe I spelled something wrong. It's fine. So we can just pop that in here, and we're good. Residual Vector Quantizer. Okay. So yeah, so this can train, and this will be fine. But while this is training, what I want to mention is why are we even caring about this? And the main reason is for an architecture like this called SoundStream. So SoundStream is a very popular architecture specifically for neural audio compression is probably the best way to think about it. So what you have is you have an audio, you have some audio, you have some autoencoder, and then you have, the audio that comes out the other end. And just like everything else, you want to make sure there's the reconstruction is good. And now to get the reconstruction good, there's a couple other things going on. Namely, they add a GAN loss to it as well, but we're not going to look at that for now. For now, we're just going to look at the fact that we have a encoder that compresses and the decoder. And notice in the middle, we have a residual vector quantizer, right? An RVQ. And so you can see here, this RVQ has n different code books inside it, right? I can't remember off the top of my head how many there were, but there are n different code books. And so what it does is, just like before, we'll get the quantized token from the first one, which is an estimation of the original continuous value. Then we're going to get a quantized token of the second one, which is an estimation of the residual, the error between the quantized one and the original. And then we get the third one, which is the error from the next set. And then we get the fourth one, the error from the next set. And just repeat this over and over again. Now, a really cool thing they do is instead of passing all of the quantized tokens, like we just added them all together, right? We just summed them all together and passed it to the decoder. To make our decoder more robust, they'll randomly sample some number of quantized tokens. So you can see in this case, they're going to say, oh, let's just add the first 4 and ignore the next 2 or something. And so this makes the decoder more robust because it needs to be able to do the same estimation problem of reconstructing our signal without with varying amounts of precision, right? Because the more quantized tokens you add, the more precise that final embedding is compared to the original one. So this is the key idea, but this actually goes into another field called audio, or basically they're called codec language models now. And I'm not going to go into codec language models too much right now, but I want to frame the problem this way. Let's say you are a database engineer, right? And your goal, right? The problem is always there's just too much data on the internet. And there's only so many hard drives you can buy to save all that data. So is there a way for me to have a reliable reconstruction of my image? Like, can I train some type of a compressive algorithm that's reliable enough for me to store my data in some compressed format and then decompress it when I need it? Right? And one great way of doing this is the residual vector quantizer. We could have also used the VQVAE, but maybe a vector quantizer, a standard vector quantizer, wouldn't give you the reconstructive performance that you're looking for in kind of a task like this, let's just say. So we need better estimations. And so imagine it this way. What are your options? In a regular autoencoder, we compress our image or audio or whatever down, but we still have some continuous embedding at the end. And so, sure, the continuous embedding here is significantly smaller in size than the original input. So you can store the continuous embedding on your spinning drives and you'll get a huge gain there. But these continuous embeddings are still float32, some precision format, right, that we save them in. So what's another option? We could, and this is specific to the RVQ, what if we have a bunch of these quantized embeddings that we've stored up, right? So we can say that, in the first quantizer, we want the third embedding, and then the sixth embedding, and then the fourth embedding, ... for each of these things. Then instead of storing the quantized embeddings themselves, all we need to do is store the indexes, right? We can just say, this audio here, or image, or whatever, corresponds to the third quantized token in the first one, and then the sixth one in the second one, and then the fourth one and the third one, ... This means in your hard drive, all you need to do is store a couple of integer values, which is a huge reduction in storage costs. Now during inference time, all we need to do is say, okay, this image was made of these indexes. So I can now go back into my quantizers, load those specific embeddings from those indexes, and then decode, right? And then basically pass the decoder and keep going. So I just want to write this method real quick, just so you get a feel for exactly what's going on, and then we'll be done. So here we go. We had something happen. We can go ahead and do a quick generation. There we go. So nothing fancy, right? I just grabbed an image. I passed it through the autoencoder. I got the reconstructed image, and ta-da, we have a reconstruction, right? Nothing crazy. What I want to do is the getting of the code, right? I want to actually get the specific codes that we want to work with. So let's go ahead and do that. So to do this, we're just going to write two quick methods. Now, these are methods we would only use during inference time, right? Getting codes and decoding specific codes. So let's just go ahead and do that. So we're going to do def get codes self x. So this would be, I pass in an image, and I will grab the indexes of which codes in each code book represent this image, this specific image in this case. So we're going to do torch.noGrad, right? Because this is, again, something we'd only do during inference time. And let's just do x as x.flatten, right? Just like before, right? We went ahead and flattened our images before we passed them in because we're not dealing with any convolutions or anything like that, just simple linear layers for now. And what we're going to do is just like before, x is equal to self.encoder x. So we're going to go ahead and store our, or we're going to compute our latent space, the continuous latent space. And then this is why in this method here to quantize, I had a flag to return the code indexes only. So that will only return these code indexes. So let's go ahead and do that. This is going to be code index is going to be self.quantize x, or we're going to pass an x or z, whatever you want to call it. And then we're going to do our return code index only equals true. And we return code index. And it's as simple as that. So now what we can do is instead of just model rand, let's do, instead of just this forward method, which we don't really care about during inference time, we can do model dot get codes, right? The method we just wrote, right? To get the codes. And what should we see? We should see that, oh, where'd it go? Here we go. So we can see for the, granted, these pictures are very similar. So right now nothing is trained and these are just random. So for every single image, there's two images. We have on the, let's just look at the first image. We see that the image, the quantizer decided that the first quantization token is the 9th one in its embedding matrix. And then the second one is the 30th one. And then the third one is the 32nd one, 29th one. So these are the indexes in my 4 code books, because again, remember, I have 4 code books. These are the indexes in my code books that my quantizers decide that it wants to store. And then again, the same thing for the second one. And of course, if we run this over and over again, we'll get different results because it's random. But here you go. So these are the indexes of the codes, or the indexes of the quantized embeddings that our model has decided. And we've just stored these. And now the cool part is, instead of storing a 32 by 32 floating point precision like image or whatever in your hard drive, all we need to do is store a couple of indexes. And that's a significant reduction in the cost of your kind of storage costs, right? How much space it takes to store your data. So we get our codes. We also need to similarly be able to decode, right? So we can do, again, at torch.noGrad, and we can do def decode codes, decode codes self, and all we're going to do is pass this the code index, right? Or the code indexes. And so let's just go ahead and create so we need to create our embedding, right? So how do we do that? What we have right now, if you remind ourselves, is the index of, in this code book, I want this code. In this code book, I want this code. In this code book, I want this code, ... So what we need to do is grab those codes, because I only have the indexes of them. So grab all of those codes, and then just add them all together, and then pass the accumulated one to the decoder. So let's first go ahead and create an empty tensor again, to accumulate our codes into, and then we have to actually grab them, right? So let's go ahead and do that. Okay, so we're going to do a quick, let's see, we're going to say batch size is equal to code index.shape 0. Let's go ahead and store that. And let's do RVQ codes is going to be torch.zeros, and it's going to be in the shape of exactly what we think. It's going to be the batch size, so how many samples are we wanting to decode, and the latent dim, right? Because this whole thing is happening at that latent dimension. So self.latent constant dim. And our device is just going to be wherever our code index.device is, just to make sure whenever you create a tensor in a model, you want to make sure this tensor is being created in the same place that is going to be interacting with other things that's being passed into the model. Good. That shouldn't be there. OK, so now that we have that, all we need to do is loop through our code. So we're going to do for index quantizer in enumerate self.rvq. We're going to loop through all of our residual vector quantizers. And we're going to do q codes is going to be code index. And so what are we doing? If you remember, right, which one do we want? We have a rerun. Let's rerun you real quick. So we have this. So we need to grab for the first code book, right? We need this column, right? So for this is the batch dimension. These are the number of code books. So these two numbers in this first column represent the codes that go to the first quantizer, and then the codes of the second quantizer, codes of the third quantizer, dot, dot, dot. So we want all the rows, but we want to just loop through it one column at a time. So we can quickly do that. That's just going to be the code index matrix, which is just this. And we're just going to grab all the rows and the index, whatever index we're currently on. Now that we have that, we can do our quantized embeddings. Quantized embeddings. It's going to be just the quantizer, right? And remember, inside our quantizer that we wrote before, we wrote a embedding matrix. And all we need is to grab the embedding of the index that we gave it. And the embedding matrix does exactly that, right? You give the embedding matrix an index, and it returns the embedding at that specific index. So we can just use the embedding inside it. So we can do quantizer.embedding, and we're just going to pass in our q codes. Simple as that. And so then, lastly, we want to accumulate these codes into that zero vector. So we do RVQ codes plus equals quantized embeddings. Simple as that. And lastly, we're going to take these RVQ codes. We need to decode them back into the actual image space. So decoder. We're going to pass in our RVQ codes. And we can then finally do decoded is equal to decoded, right? We want to put it back in the image space. So decoded dot reshape batch size, and then we know is 1 by 32 by 32. So I'll just do that for now. Decoded. Good. So now this is the method to get codes. These will give me codes. And then we'll have the method to decode these. So that's going to be our model.decode codes. And we're going to pass in our codes. And there we go. We got back our original image space. We can do .shape, right? Got everything back. So we are now good to go, right? Now we have the method to get codes and decode codes. And this is, again, there's a lot of applications for this. Again, audio codec models is one of them. Data compression and storage is another one of them. But for now, we're just kind of doing it this way. So I think we'll have to retrain this model super quick. OK, I will cut the video. I'll come back in just 2 minutes. Nice, and that's basically it. So I've went ahead and just cut ahead. So as you can see, it's the same generation script from before, except what we're doing now is we are grabbing an image, passing it, we're grabbing the codes of that image, and these are the codes that it determined that it should use. So it's saying that in the first embedding matrix, use the 37th code. In the second embedding matrix, use the 34th code, ... right? And what you would do is you would store these integers inside your hard drive. During inference time, all you do is load your model, grab your integer code indexes from your computer, and then pass it to my decoder, which will just go ahead and decode it, accumulate everything up, pass it to the decoder, and give you back the original image. And this is just a very, very high-level idea of the residual vector quantizer. It's all I really wanted to talk about today. It's supposed to just set the stage for some more advanced models that I want to go into in the future, namely SoundStream, the Codec model, a lot of stuff. Specifically audio models seem to use this a lot. I haven't seen it a lot in the vision literature. I'm sure it's there. I just haven't seen it. But either way, I'm going to call it here. I hope this was helpful. If you have any questions, go ahead and drop it down in the comments below. But I will see y'all in the next one.